Hello, students. This is the second lecture of the indexing lecture series. Today we're going to talk about hashing. And last time we talked about the B tree, and I told you the B tree is the most important data structure in the database system. Today we're going to talk about hashing, which is the second most important data structure in database systems. Okay. Um, As I said last time, what would be a data structure? So if I have to give a one sentence summary, it would have to be a way to organize your data with the objective to support certain operations efficiently. Now, pay attention. It doesn't really make sense to talk about data structures unless you know what are the target operations you would like to support. For hashing, we'll be talking about dictionary search. So let's see what this is all about. We got a set of elements. So I assume these elements to be integers, and I also assume that dictionary search is given a query. So you have search value here, and the purpose of this operation is to just give a yes or no answer regarding whether the search value Q is in the input set or not. So why is this called dictionary search? Because if you consider every integer in the input set as just sort of like an English word, here it's like you are looking up a particular word uh, and you try to find out whether this word is inside the dictionary or not. Last time we talked about range queries. So let's recall that range query um, is given an interval from Q1 to Q2, and a range query returns all the integers in the input set S that are covered by the interval. Well, if Q1 and Q2 they are identical, and then the range query reduces to what is known as a point query. Okay, so it's no longer an interval here, it's a point. And a point query is just a dictionary search. All right, so a dictionary search is sometimes also known as a point query. Okay. Here is one example. Suppose you have an input set as shown here. Okay, all these integers. So if the value of Q, the search value is 80, and then the answer is no, obviously 80 is not inside the set. And how about 81? At the 81, it's here, so the answer should be yes. Okay, so you get the idea. Well, the B tree is also able to answer dictionary search. Why? Because, the B tree is able to answer range queries, right? But dictionary search is just a special case of range query. So here on this slide, I compare the performance guarantees you have for the B tree with those that we are going to establish using hashing. So once again, you have n elements, and as before, I use lambda to represent the block size. Okay. So you have to always remember if this is the case, and then how many blocks would you need in order to store the set S, right? So you need big O of n over lambda blocks to store S. So last time I said every time you see a big O, so your instant reaction should be like replacing this big O with less than or equal to, and then there is a constant C here, and then followed by whatever that is inside the parentheses. So essentially, this says the number of blocks that you need in order to store S. This is the minimum number of blocks you need is at the order of n over lambda. And therefore, this is the amount of space we aim to achieve also for data structures. Okay, now pay attention, this is n divided by lambda. And in particular, this is not n. So if you use n blocks to store n integers, it's a huge waste because essentially you're saying every block contains just a single integer. You are really, really wasting a lot of space. On the disk, the linear space should be understood as n over lambda blocks. Okay, so this is understood as the linear number of blocks. All right, so this is very important. Now, for the B tree, as I explained last time, each B tree is parameterized by this small b, and the small b basically says how many elements you can squeeze into one node. Well, in reality, this b will have to be set to be as large as possible, subject to the constraint that the information of a node can be stored inside one disk block. So with simple calculation, you'll be able to get that this b is at the order of lambda. Okay, so we use big theta to represent the fact that b and lambda, they're always within a certain constant factor of each other. So if that is the case, and then you can verify that the space consumption of a B tree is n over lambda blocks, and this is very good guarantee because this is the linear number of blocks we aim to achieve. And furthermore, if you use a B tree to answer a dictionary search, and then you will be doing log-based lambda of n, and this is basically the height of the tree. So that's also the number of IOs that you have to pay, even in the worst case. So this is the update cost, and you are able to support an insertion and deletion in a B tree using log-based lambda of n IOs. Okay, great. So that's those are the guarantees of the B tree. Well, today we will achieve the following guarantees in terms of space consumptions. Once again, this is going to be n over lambda. So again, this is a linear number of blocks, which is great. Regarding dictionary search, before it was log-based log-based lambda of n, but now it is constant. So this is smaller than what you will be getting from a B tree. There is a caveat, though. The caveat is that, as you will see, hashing is a random process. So sometimes the cost of the dictionary search will be higher, and other times it will be lower. However, on average, you're able to prove that the cost is bounded by a constant. So this is what we mean here, that by saying that the dictionary search is actually constant in expectation. Okay, so this expectation is over the random choices made by the algorithm we use to construct the hash structure. Now, regarding update, interestingly, you can also prove something like constant, and this compares favorably to what you will be getting from a B tree. So that's not a constant, so it's lower. However, once again, there is a caveat. Actually, I would say there were two caveats this time. So first of all, this is something in expectation, and the expectation is sort of like average over all the random choices that are made by the algorithm. And also, there's another mysterious word here, amortized. This basically saying this update cost is not guaranteed for every single update. You would have some updates requiring higher costs. However, if you look at the average update cost, the average cost of all the updates, and then I'll be able to show you that it will have to be bounded by a constant. So this is the meaning of amortized. So later at the end of the lecture, all these guarantees will be stated more formally. But the big picture is what I presented. So this comparison would make you feel that hashing seems to be the winner here. Well, in some sense, it is. However, you also have to understand this is strictly about dictionary search. The B tree, on the other hand, is a versatile structure. It's able to handle also predecessor search, successor as well, and also, importantly, range queries. With hashing, however, we're not able to support any of these operations. Hashing is basically a data structure that's designed specifically for dictionary search. All right, now let's start with some basic definitions and properties. Well, for our discussion today, I'm going to use this notation a lot. So in this notation, you can see there is a value x and then surrounded by a pair of square brackets. So here, this notation represents the set from 1 to x. By the way, the set of integers from 1 to x, okay? Well, today I'm going to be very explicit about what is the maximum possible integer that we can be given. So here, this is u. In other words, we will accept only integers from 1, 2, 3, all the way to u, okay? So this is not an unreasonable assumption. Why? Because in practice, for example, every integer gets represented by maybe 4 bytes, which is 32 bits. So indeed, you only have 2 to the power of 32 different integers there, right? So you can set this u to 2 to the power of 32. So for those students that are really into theoretical computer science, and then you know that the RAM model, in the RAM model, every word has a finite length. So there is this parameter W representing the number of bits in a word. So one integer is represented by a word. So essentially it says, the maximum integer that you can represent is 2 to the power of W. So anyway, today we don't have to be bothered by the word length W. To cut a long story short, it's a reasonable assumption to consider that every integer is from some finite range. And this range u from 1 to u, and this value u is known in advance. Okay. Well, in the B tree, this assumption, strictly speaking, is also reasonable because you cannot assume that an integer can be arbitrarily large because you cannot even represent it in a computer otherwise. Nevertheless, in the B tree, we didn't have to be talking about this value u because we would not need it in the analysis. However, for hashing, if you go for a rigorous analysis, as you will see, this is something we'll require. Well, enough with the assumption. Now let's talk about hashing. To be honest, hashing is deceptively simple. I said deceptively simple. It's actually not simple at all. However, many people, they feel that hashing is simple. I guess that's because they didn't really bother to look at the analysis. Okay. Well, indeed, if you do not look at the analysis, hashing is quite simple in the following sense. Well, imagine the following strategy. Suppose somehow I divide the input set S into a lot of different subsets. Okay. Now, pay attention. This is partitioning. This is division. In other words, every element will go into one exactly subset, and these subsets are disjoint. Okay. So you can imagine sort of like every subset being a bucket. We use a bucket or barrel to contain a lot of elements, right? So instead of saying subset, that's not fancy, I'm going to say bucket, okay? All right, so you can imagine a lot of buckets there. Every element in the input set goes into one and exactly one bucket, okay? So you will have to perform the partitioning in such a judicious manner so that when at the time you perform dictionary search, you only have to search exactly one bucket. Okay, so this is the rationale. So let me emphasize that you want to make sure that the partitioning or the division is done in such a manner that when at the time you perform dictionary search, you only have to look at exactly one bucket. Okay, if you have to look at two buckets, it means that you have done something wrong with the partitioning. So how do we achieve that purpose? This is done using a hash function. So a hash function is really an h, and this h takes some value, let's say x small x, and this x, I'll often use the word key to refer to this x value. This is also a standard term when you talk about hashing. So you give me a key, okay, and then I compute the hash value of this key. Okay, so this key needs to come from the integer domain that we agreed upon. Okay, it's not something that's arbitrarily large. Okay, it has to be from a finite range, and the output of this hash function, this hx, is an integer from one somewhere an integer somewhere from 1 to m. Okay, so this m is essentially the larger the m, sorry, is the number of possible buckets I can have. So earlier I said every bucket is a subset, right? So now I will be cutting the input set into m buckets. Okay, so this hx determines, okay, if you have this element x, and then this element x will be going to which bucket? So the bucket with ID hx. Okay. So from now on, I'm going to refer to this hx as the hash value of this key x. Okay. So here we have the formal definition of what it means by a hash structure. And as you can see, a hash structure is parameterized by two things. First, you have to tell me how many buckets you plan to create. And also, you have to give me a hash function. So this hash function basically allows me to do the bucket assignment. So instead of going through the gory details here, let's look at an example first. So here I have an input set. As you can see, these are the elements. So someone says, we'd like to create 5 buckets according to this hash function. So as you can see, this modulo operator, you'll be seeing this modulo operator a lot today. So this modulo operator basically says you want to do integer division. So for example, x divided by 5, but you want to get a remainder, okay, remainder. So the remainder goes from 0 to 4, okay? So if you also add 1 to it, and then you get a hash value from 1 to 5, and this is exactly what we promised, because we say that the hash value will have to go from 1 to 5. Good. So here, this is what it looks like, okay, a hash structure. So you have got 2 parts. So this is called a hash table. Okay, I'll explain the content of the hash table later. But here you can see I have 5 buckets. Okay, so each bucket is a subset. For example, L1, if I say what is the subset L1, then you should say, hey, the subset contains only one element, that's 75. And how about bucket number 2? It contains 2 elements, which are 81, 56, etc., etc. And you can also have an empty bucket here. As you can see, there's nothing there. All right, so how do we create the bucket? Well, that's easy. So if you look at the first element, which is 34 here, so you calculate what's the hash value of 34. So let's just do the math carefully. So you're looking at modulo 5, right? So you do that, you get 1 plus 4, which is 5. So which is why you can see that 34 goes into bucket 5, okay? And 19, so this is the second element here, you calculate the hash value, you get 5. Okay, 67, its hash value is 3, which is why it goes into the third bucket. Okay, you got the idea? All right, so essentially, you would like to group all the elements by their hash value. Okay, so what can you say about each bucket? For example, bucket L1. So this consists of all the elements in the input set whose hash values are equivalent to 1. All right, so that's the definition of L1, and similar definitions can be used to define the other buckets as well. Now, let's talk about the hash table. So the hash structure overall, this is a disk-oriented data structure. Okay, let me repeat, disk-oriented data structure. So this means, all these buckets will be stored on the disk. Well, this is simply just a file. So we have 5 files here, okay? Well, every file has a starting address, right? So you have to remember the starting address of the file. So this is the way for you to be able to retrieve the file, the beginning of the file, and then you get from the beginning, you can continue to read the file if you want, okay? So where do we keep the addresses of these files? Well, that's the hash table here, okay? So the hash table is an array, and so this array has 5 cells. So each cell stores, actually I will have to emphasize that the ith cell, okay, so this is the ith, okay? So this is 1, 2, 3. As you can see, the ith cell stores the address of the file regarding the ith bucket. Okay, so this is this is the third cell, number 3, right? So this is bucket number 3. Now you can see this is true for every single bucket. Okay, nice. So I hope you have got some great ideas, clear ideas about the hash structure. So let's go back to the formal definition. Now remember, I want to emphasize, no matter how many examples you look at, there's no replacement for the formal definition. So don't blame me for having to, and don't blame me for insisting that we talk about the formal definition here. Okay. So once again, you need 2 parameters for a hash structure. The first one is the number of buckets, and the second one is a hash function that you want me to create those buckets for you. So consists of 2 components. The first one is a hash table and also the buckets. Okay. So let's talk about the buckets first, right? As I defined before, if you look at Li, this is the ith bucket. It includes all the elements in the input set whose hash values are equivalent to I. Okay. So once again, you want to group the elements by their hash value. Okay. So this is the meaning of a bucket. So you have m of them. Okay, so m of them. Well, every Li, as you can see here, is stored as a file. Okay, and the file is stored on disk. In order to find this file, you have to remember its address. Okay, where is this address kept? Well, this address is kept in the hash table, and more specifically, this is an array. So as long as you give me I can go to, I'm sorry about that. So you can go to the ith position of this array to fetch the address of its file. Okay, so let me emphasize this is an array, and this is still stored on the disk. But how do you store an array on the disk? Well, this is done by storing the hash table using consecutive disk blocks. Consecutive, all right. Just like in the internal memory, you want to store the cells of the array consecutively. Okay, so here, same thing on the disk. Well, this is an important slide because this slide tells us how to calculate the amount of space that you need in order to store the entire hash structure. So here we will need a few notations. So once again, this n is the number of integers in the set S. Number of buckets, we already know that, and this is the hash function. So as usual, this lambda refers to the block size. Okay. So now let's look at the hash table first. All right, so the hash table here. Now remember, a hash table goes like this. Um, you have how many entries? You have exactly m entries. Okay. So each entries is an address. So how many bytes do we need to store an address? I would say today we are using 8 bytes, right? So if you can store 8 bytes, I'm sorry, if you need 8 bytes to represent an address, and a block has lambda bytes, right? So how many entries can you pack into one block? Well, the answer is lambda over 8, right? You also need to be taking the floor, okay? So this is how many entries of the array you can pack into one block. So how many blocks do you need in total? Well, obviously you need so many blocks, right? And this could be a fractional number, so you have to round things up, okay? So this is exactly what you get here, okay? So this is how much space you would need in order to represent the hash table. Very nice. So now let's look at a bucket. So a bucket basically says, let's say this is the ith bucket we're talking about. Okay, so this I here, right? This I here. So here we have a file, this is li, right? So the li is stored in a sequence of blocks, right? So it's a file. So how many blocks do you need? Well, that depends on the size of li, okay? How many elements there are inside this bucket. And also it depends on this B. So this B is how many elements you can fit into one block, okay? So if B is an integer, I'm sorry, if the elements are integers, and then you can calculate this B as sort of like lambda over 4, assuming 4 bytes are needed to represent an integer, right? So in general, we don't want to emphasize the constant 4, so we simply say B is big theta of lambda, okay? So I don't know how good you are with the asymptotic analysis, but for here, it suffices to understand that this B and lambda, they are within a constant factor of each other. And the constant factor, as I said, is 4. Okay, so next time you look at B, you can just think about lambda. Okay, essentially you are correct, and you are correct asymptotically. Okay. So continuing, as I said, in total, you have Li, size of Li elements, and each block will allow you to store small b elements. So if you take the ceiling, and this is precisely the number of blocks that you need in order to store everything. Everything in this bucket. Okay. Now, if you add up what we have already calculated, so this is the number of blocks needed for the hash table. This is the number of blocks that you need for one bucket, and then you do the summation here, okay, over all the buckets. And then this is the total number of blocks that you will need. So you do some calculation, and some calculation that is rather rudimentary, and I'm not going to talk about that. And then in the end, you will get this expression here. Okay, essentially saying you will be using m plus n over lambda blocks, okay, up to a certain constant factor at most. Okay, so I want to quickly convince you that this is quite expected. Okay, so look, let's look at each bucket, right? So let's say the ith bucket here, right? So you might have very few elements. Let's say even if you have just one element inside this bucket, you still need one block, right? So in a hash structure, the buckets are stored separately in different files. So no matter you like it or not, you will need at least one block to store each file. So in other words, here you might be wasting one block, in other words. Okay. once again, even if the bucket has only one element, you have to use one block anyway. All right, so you might have one block that is extremely underutilized, but you have to do it anyway. So if you look at this, in the worst case, you should be prepared to waste M blocks on the disk. So this is intuitively why you will have an M here. Now, on the other hand, this M over lambda captures the fact that you will have to store n elements. And let's recall that this n over lambda is considered the linear cost because this is the smallest number of blocks you will need in order to store n elements up to a certain constant factor. Okay. So overall, this explains why the space complexity is m plus n over lambda. So this calculation tells us that it's not such a great idea to increase the value of m indefinitely. So at some point, you know that the value of m should not be set any higher because that will force you to use more space. So in practice, this value of m is almost always set to some value that is at the order of n over lambda. Okay. As you can see, you have this big theta here. So once again, this big theta basically tells you that m and n over lambda is always within a certain constant. Okay, so there is a constant c here. And later on, you will see how to set the value of c. So we will be able to talk about this only after we have talked about the analysis. But one thing for sure, regardless of this constant c, as long as it's a constant, which has nothing to do with this n and lambda, and then you will be able to prove that this m plus n over lambda is simply just big O of n over lambda, right? So there is some constant here. Okay. So when I explained the intuition behind this calculation result, I did not really talk about the hash table itself. Why? Because the hash table itself is actually very small. Okay, so you can see the hash table contains only m integers, and the value m is significantly less than the n here. Okay, how much smaller? Actually, it's smaller than n by a factor of lambda. So in terms of blocks, it also goes down by a factor of lambda. As you can see, it's the hash table itself only occupies n over lambda squared blocks. Okay, so you don't really have to worry about the hash table. Okay, very nice. Now we already know how to define a hash structure. Next, we'll see how to use the data structure to perform dictionary search. Okay. So let's look at an example first. Still the same input set and also the same values for m and the same value for m and also the same choice of hash function. Right? So this is the hash function here. Now let's look at dictionary search and let's say we're looking for 57 here. What's the reasoning? The reasoning is, well, if 57 was indeed in the set. And then we'll have to go into which bucket. Well, you calculate the hash value of 57. So this is 1 plus 57 modulo 5. So this will give you 3, right? So the reasoning is if 57 was indeed in the set, and then it will have to be inside bucket L3. All right. So let's just scan the file of L3. But hey, you have to know the address of the file first, don't you? So that's why you want to go and access this particular cell. Okay, so this is the place where the address is stored. Okay, so you go there. Now, if this hash table is stored on the disk, you will have to pay 1 IO to read it. Okay, and remember we don't have to read these two cells. we can go directly to this cell because this is an array. The hash table is an array. So you might want to ask, how do we know which block contains the address for bucket number 3? Well, you do because the hash table is stored in consecutive blocks. So, and you also know how many addresses fit into one block. So now you can do the math, right? So this is a 3, and you look at this 3, and you look at this number of addresses that fit into one block, right? So from there, you can figure out, which block in the hash table contains the address you're looking for. Okay. So now you understand why the hash table must be stored in consecutive blocks. So you get the address of the file, and then you want to go and open up the file and read it until you find 57 or until the end of the file. Okay. So in this case, we read the entire file and still we don't see this 57. So this is the reason why we're able to conclude that 57 cannot be in the set. Okay. So importantly here, we don't have to search anything else. We don't have to look at the other 4 buckets. Okay. So this should echo my claim earlier, when I talked about the rationale behind hashing. I said the rationale is to partition the input into disjoint buckets, but you have to do it in such a judicious manner, such that when you perform dictionary search, you only have to search one bucket. So now if we always group the elements by hash value, and then this provides exactly what we need when we perform dictionary search. You only have to search one bucket. Okay. So this is a neat and elegant idea. All right, now let's go back to the formal description of the algorithm. So here, this is the algorithm. It says you use the search value to compute a hash. Sorry, you search value Q, right? And then you compute the hash value of Q. Okay, and then that tells you the ID of the bucket that you have to search, right? So just read the bucket, and if you find Q there, obviously you should answer yes. Otherwise, you can safely conclude the answer is no. Now, let's talk about the I/O cost. Well, there are 2 parts here. First of all, you will need to definitely pay an I/O to read the address of the file that you want to scan. So that explains this 1 here. And then you also have to scan the file. And the number of I/Os that you need in order to scan this file depends on how many elements there are, how long this file is, right? How many elements there are inside this in this file. So in general, this is the number of elements you have in the bucket. So this is the bucket size, and each bucket can store lambda values, right, up to a constant, right? So this is the number of blocks that you need in order to read this file. Okay. So overall, this is the I/O cost. Okay. Good. Well, let's look at another interesting example. So in this example, I changed the hash function. So this hash function says, no matter what you give me, regardless of the key, the hash value is always 3. Well, I know this sounds stupid, but you'll see the point that I'm trying to make. Well, again, with this M and also this H, you are able to create a hash structure, and the hash structure is right here. As you can see, indeed, you have 5 buckets. And you look at the contents of those buckets, you will see bucket number 3 contains everything. This is not a surprise, right? Because the hash values of all the elements are equivalent to 3. So you insert all of them into bucket number 3. Okay. The other buckets are simply empty. So When we perform dictionary search, let's say 57, what do you have to do? You calculate hash value. Hash value is 3. And therefore, you go to bucket number 3 and you start scanning, and you see basically the entire input set, entire data set. So you pay a huge I/O cost. The I/O cost is at the order of n over lambda. Okay, n is the total number of elements here. So what's the implication? Well, you can see that the hash function is a really, really bad function because it's such a stupid function that puts everything into simply one bucket. Okay. Now you know when you do hashing, you want to make sure that the hash function is a good hash function so that it can distribute the elements into different buckets as evenly as possible. So the best you can do is, you have m buckets, and if you really go for an even distribution, and then every bucket should be containing roughly n over m elements. Okay, and intuitively, this is going to be very nice because, as you know, we set m to be roughly n over lambda, right, up to a certain constant factor. So if you plug this in, then you see that this is at the order of how much? This is simply saying every bucket has roughly lambda elements. So this is very good because the lambda elements fit in a constant number of blocks, right? So once again, every block contains lambda elements up to a constant. So this further means that the search cost is going to be very good, sort of like constant per query. Okay, so that's the implication, right? So you will have to use a good hash function to make sure that you can distribute the elements as evenly as possible. Okay, and if the hash function is terrible, such as the case here, this is such a bad function, and then the dictionary search cost would be as bad as n over lambda. Okay, so this generates a very important question. Now, how do we choose a good hash function? Okay. Well, this is the place where a lot of people, I would say, have misunderstandings about hashing. So of course, the hash function that I use here is extremely stupid. This is quite obvious. Nobody in practice will be using a hash function like this. So if they have to implement hashing, I think it will make sense to use a more complicated hash function. So such as this one. This is more sophisticated, but you can have your creativity here. You can make it even fancier, even more complex. Okay. But interestingly, if you always use just the same hash function, I can tell you, your hash function, in the worst case, is going to suffer from exactly the problem as the hash function in this example. In other words, if you think that this hash function is stupid, and then it's equally stupid to be using a single hash function always for all the data sets. We will explore this topic further in the tutorial. But the takeaway message is that you should not be using just a single function, because no matter which function you use, however creative you believe you have been in designing the function, in the worst case, you will always suffer from the same issue as the stupid function you are seeing on screen right now. And the issue is you will be putting all the elements into the same bucket so that the hashing achieves no purpose at all. So this is the point where we start to talk about the theory behind hashing. So the theory, honestly, is not easy. It's not trivial. So if you can understand the theory, it's going to be excellent, and you have every reason to be proud of yourself. Okay. So I just want you to know that I'm not going to test you on the theory in the quiz. However, if you want to excel, if you want to stand out from the crowd, I highly encourage you to look into the theory and understand everything I'm about to say, so that you can get thorough understanding. Okay. Well, as you will see, I will also be talking about some algorithms. Even if you don't care about theory, you will have to understand those algorithms um, so that you can use hashing properly in practice. So one strong message I should have delivered is that you should never stick to just one single hash function, because if that's what you do, I can always give you an input. I can always give you a data set such that your hash function will end up putting all the elements into the same bucket, and that's horrible. So let me tell you um, uh, what is a much better approach. So the better approach is to prepare a lot of hash functions. So we call this a family. So whenever I say family, essentially that's another way to say set. This is a mathematical term. For our discussion, it suffices to consider the term as a synonym of set. Okay, a set of hash functions. So we call this a family. So in general, if you have a family like this, I will use this beautiful H, this H, the font, right? So it's a bit curly. Okay, so this is a beautiful H that I'll be using. So this refers to the family of hash functions that I'll be using. Okay, so the idea is when I need to create a hash structure, I will always randomly choose a hash function from the family. Okay, so this is why hashing the hash structure, so I should say the construction of the hash structure is a random process. Why? Because it will become deterministic only if I have already chosen a hash function. So from this point and on, the construction goes deterministically. However, this is sort of like the seed of everything. By choosing so when I make the choice, it's a random choice, and different choices will lead to different hash tables. Very good. So in this case, we get to talk about a very, very important property, and this is called the universality property. So if you think about it, let's focus on two arbitrary keys. Okay, so the first is K1, the second is K2. Well, obviously, if K1 and K2 are the same, and no matter what hash function I choose, they will always go into the same bucket. So that's why we focus on the case where K1 and K2, they are distinct. So intuitively, you ask yourself, right? Do you prefer this K1 and K2 to appear in the same bucket, or they are in different buckets? I don't know about you. For me, the answer is obviously they should appear in different buckets. That would be a good situation for me. Why? Because imagine, right? So one is query and one is element, right? If I am looking for query and if K1 and K2, they belong to the same bucket, and then I will have to go to the bucket to look for K1, even though K1 is not there. But I still have to read something like K2, and that's not a very nice thing when it comes to the IO cost calculation. So indeed, in this case, we say there is a collision. There is a collision in hash values, right? So once again, collision happens if K1 and K2, they are two different keys. However, their hash values are the same, right? You have to bear in mind they are different, right? If they are the same thing, as I said, their hash values are definitely be the hash values will definitely be the same, right? But if they have distinct values, then and also their hash values are the same, and then we say a collision happens, right? So if you think about it, there are m buckets in front of you, and even if you throw every key to a excuse me to a random bucket, you believe that the probability should be something like 1 over m for a collision to happen, right? So this is very intuitive. Well, interestingly, this is exactly what is required by the universal property. Okay, the universal property says the following: Now, if you think about this collision event, now, first of all, this is a random event. Why is it a random event? Because everything depends on what is the hash function I choose, right? So if I choose a hash function, which happens to make K1 and K2 have the same hash value, and then collision happens. But if I happen to choose another hash function where this is not true, and then this random event does not happen, right? So it happens sometimes, it does not happen in other times. So the universality says, well, the probability for this event to happen will have to be bounded by 1 over n. Okay, so the probability, why do we have probability here? Because this is saying, this random process. This is talking about the random process here, right? H is randomly chosen. Okay. So in other words, if you talk about this particular event, K1 and K2, right? So in your hash family, you should only have a very small number of hash functions that will allow the collision to happen. Because as you can see, this hash function is chosen uniformly at random. Okay. In terms of fraction, it cannot be more than 1 over n. Okay. So this is the idea. So next, I'm going to analyze why the universality assumption will allow us to prove that the dictionary search has very good cost, actually has constant IOs, will require only constant IOs in expectation. Okay. So let's review some symbols together. We'll assume that the set S contains n integers. And also, once again, lambda is the block size. Okay. So the number of buckets is m, and we are determined to make m proportional to n over lambda. Now remember, this n over lambda has very special meaning. N over lambda is the smallest number of blocks that you need in order to even store the data set. So we want to do, we want to achieve the linear number of blocks for the data structure, and then we have to set this m to be proportional to n over lambda. Okay, so this is something I already explained. So here, this is C is a constant. Okay, so it can be any constant. Good. Well, we will assume that this beautiful H is a family of hash functions with the universality property, universal property. And we will be choosing a hash function H uniformly at random. Okay, and then I'm going to show you if this is what you do, and then indeed you can guarantee that the search cost is constant in expectation. So now let's think about a dictionary search. All right, so this is the search value that you give me. Well, I'm going to focus on the case where the search result is negative, which means the search value is not in the set S. Well, intuitively, I'm looking at a more difficult case here because if you if you are indeed able to find the search value Q in the set S, and then intuitively you do not have to exhaust one entire bucket. So you expect that if the answer is yes, and then the cost is not going to be as high as the cost of the no case. So I will be analyzing the more expensive case here and leaving the yes case, the opposite case, which means Q is inside S, to you. Well, as analyzed earlier, if you look at the process of dictionary search here, and then the cost is 1 plus the number of blocks that you have to search in the bucket. Okay, so I want to remind you that this HQ is the hash value of Q. So this is the ID of the bucket that you have to search. So you do that, and you want to look at everything inside. So this is basically the number of blocks that you have to read in the file, okay, up to a constant. But you have to read one block anyway, even if this bucket contains just one single element. So there is a 1 plus here. So as you can see, it suffices to analyze the expectation of this term. Okay, so we want to analyze the expectation of this term here over lambda. Okay, so this is what we want to analyze. And clearly this lambda is not a random variable, right? So you take it out. So this is essentially saying you want to analyze this quantity here. So this is saying the size of the bucket, how large is this bucket in expectation? So if you think about it, what do you have inside the bucket? Well, think about collisions. So every element inside this bucket has a collision with respect to Q. In other words, all those elements, they have the same hash value as Q. So we can calculate the size of the bucket as follows. So we look at every element EI. So this element EI either appears or is absent from the bucket, right? It is either present or absent from the bucket. So if it's in the bucket and then it increases the size by 1, the bucket size by 1. If it's not in the bucket and then it increases the size of the bucket by 0. So for this reason, let's introduce a random variable, and this is a 0 or 1 random variable. This is called an indicator random variable. So indeed, if EI and Q, they are inside the same bucket, which means their hash values are the same. And then I'm going to define the random variable to be 1, otherwise it's 0. So this allows us to represent the bucket size as a simple summation. So this summation is simply over all the xi's. So take a moment to verify that this is correct. So remember, this is what we want to analyze in terms of expectation. So let's do a little bit of derivation here. So you can see this is the bucket size that we care about. So you can push. So, okay, let's do one more step though. And then this expectation of xi. And then by linearity of expectation, you can take the expectation out. Oops, I'm so sorry. Actually, I was going too fast. Sorry about that. Sorry about that. I should have said, this is what I wanted to say, okay? So for here, you simply plug this definition into this place, okay? Now you apply the linearity of the expectation. You can push the expectation in to the summation, okay? So this is what I'm going to analyze next. Once we know what this is, and then we can do the summation. Okay, now let's look at this expectation. And here we're applying the definition of the expectation. This is an indicator variable, so it takes only the value of 0 or 1, right? So in general, if you calculate the expectation, this is the formula you want to use. 1 times the probability of taking the value 1, 0 times the probability of taking the value 0, right? And then this term, obviously that is 0, and this term, this 1 does not matter. So this is precisely the probability of xi being 1. But what is the probability of xi being 1? Now remember, this xi being 1 essentially says there is a collision between EI and Q. So now the question boils down to the following. If I choose a hash function randomly from this beautiful family, and what is the probability that I will have a collision event between EI and Q? So this is precisely something that is from the universality assumption, universality property. So our beautiful H has this property, universality property, and therefore we know from the definition of universality that the probability of this is at most 1 over n. So that's how we got this part. And now you plug this in, and so we are able to get a very nice fact. So the expectation of xi is bounded by 1 over n. So earlier I showed you that if you want to analyze the expectation of this, essentially this is the sum of n expectations, and this is repeated here. So for each one of them, we're able to bound it with 1 over m. So now we can get an upper bound on the sum. So that's n over m. So let's not forget, this is only the bucket size, but we care about the number of blocks required to store the bucket. So we have to divide everything by lambda, and that's the I/O cost. So that's why we now analyze what happens to the number of blocks that we need to store the bucket. Okay. So this lambda is taken out here. So you have this 1 over lambda. So this basically takes care of this lambda here. And now you want to plug in this n over m into this position, right? On the other hand here, what I did is I also took care of the value of m. So I substituted this m with the value it should be taking is a c times n over lambda. So that's how you got this term here, okay? So the nice thing is everything cancels off each other. So you are left with 1 over c. Okay. So now with everything combined, we're able to conclude that under the universality property, you are able to prove that the expected dictionary search cost is 1 plus this term that we just analyzed. And the 1, of course, stays here, but this term is something that could be made very small. So this is a big O of 1 over c. Okay. So remember, the value of m is set to c times n over lambda. So now we are able to explain a trade-off between the space and the dictionary search cost. Okay, the dictionary search cost is essentially the query cost. So I would say a trade-off between the space and the query cost. So now remember, this is the space. The space is this m plus n over delta. So if we choose a large value for c, then you can see we will be using more buckets. If we use more buckets, and then the amount of space goes up. So you can see that if C increases, and then the space consumption increases. So that's a bad thing. On the other hand, if you use a larger number of buckets, and then the expected search cost goes down. So that is a good thing. And therefore, this creates a situation where you would like to consider two contradicting factors. So how much space are you willing to invest? And subject to that threshold, you would like to set the value of C accordingly. Well, the trade-off that I just explained can also be understood in a different manner. So I explained earlier that if you have m buckets, for every bucket, you should be prepared to pay 1 block anyway, even if this bucket contains just 1 element. You still have to use 1 block to store its file. So this explains the m term here. So as you can see, if you increase the number of buckets, and then you must be willing to waste a lot of empty space here, because you will be having a lot of empty space in the block if the bucket contains just 1 element. So that's why it's from the perspective of space consumption, it's not a good idea to increase the value of m. On the other hand, if you increase the value of m, you can imagine that the elements will get spread into more buckets. So on average, one bucket will contain fewer elements. And therefore, when you increase the value of m, it benefits dictionary search. So the cost of the dictionary search goes down. Okay. So it's a trade-off. All right. So this is the principle for choosing the value of C. Okay. So in practice, I would say the value of C should be something somewhere like 2 and 3 so that you can strike a good balance between these two factors. Okay. By the way, just to remind you that the hash table is actually very small, and this is not really the bottleneck in the space consumption. Okay. And sometimes a database system will even store the hash table in the main memory. Well, now, even if you don't care about the analysis, as I said, I will not test you on the analysis. You still have to understand how to construct a hash family. Now, this is the algorithm part. While you don't care if you don't have to look into the proof, and then this algorithm should be fairly accessible. So it says the following. Now I'm going to define a hash family like this. So look at this hash function here. So this alpha and beta are two coefficients, which I'll fix later. But suppose I have some value for alpha and some value for beta, and then this becomes a very specific and concrete hash function. So you take the key, and then I will calculate things like this, right? So this is multiplication. Now this is a coefficient. It's a constant. Remember. So I multiply this, and then I shift it by beta, and then I take the modulo with respect to p. I forgot to explain this p. So p is a big prime number. How big? Well, this prime number will have to be larger than u, will have to be larger than m. Of course, in practice, this m, the number of buckets, is way less than u. So typically, typically u is way larger than m, and therefore this prime number essentially will have to be something that is greater than u. So u is the maximum integer that you can represent. Okay, so continuing, I said this alpha and beta, right? They're coefficients, and once they are chosen, and then you have a concrete hash function. Now let's see, alpha times k, so that's the first thing you like to calculate, and then you want to shift it by beta, and then you want to calculate the modulo with respect to p, so basically this is taking the remainder when you divide this thing by p. And then you get this thing, just already feels quite chaotic, right? And then you want to take everything, you want to take the modulo with respect to m, right? You want to divide this whole thing by m, and then you take the remainder. Okay, now finally, you want to add 1 to it, so that you will get a value in the range from 1 to m. So this is what we promised. So as I said, every choice of alpha and beta will define a concrete function. So how can I choose alpha? Alpha is chosen from this set. So you have p minus 1 different choices for alpha. For beta, you have p choices. Okay, so all in all, you have how many choices for alpha and beta combined? You have p minus 1 times p. Okay, p minus 1 times p different choices here. So this is the size of the hash family. As you can see, this is a large hash family. So when you want to choose a hash function randomly from this H, all you have to do is to choose this alpha uniformly at random from this set, and then beta uniformly at random from this set, right? So this can be done in constant time, CPU time, right? And after that, you have a concrete function. So this is the random process that should be happening before you construct the hash table. And you first do this random choice, and then you proceed to construct a hash table. And then you will be able to guarantee this constant search cost, constant IO search cost for dictionary search. So one remaining question is why does this universal family have the property of universality? Okay, so this is proved in the appendix. I have an appendix here just for the sake of completeness, but I can tell you this is way beyond the scope of this course. Right? You are not required to understand the proof. Actually, the proof is rather difficult. It's based on number theory. Okay, but it's included here for those students that really want to get to the bottom of this. Well, one comment concerns the existence of this P, because some students would say, hey, you see this prime number is so big, can I always find such a prime number? Well, the answer is absolutely yes. So number theory says you look at any x and any 2x, there must be a prime number there for sure. Okay, so we know this u is a fixed number. It's a finite number that we know in advance. So all you have to do is to prepare a prime number that is between p and 2u. Between u and 2u, and you can prepare this number in advance, right? In an offline stage, and then use it forever. Okay, so this is not really an issue. Okay. All right. So it's been a long lecture, and now we will continue to talk about updates. So far, you know what a hash structure is, and you know how it can be used to perform dictionary search. But as I said, a hash structure supports 3 operations, right? Dictionary search, that's one, but also the other 2 operations are insertions and deletions, respectively. So next, we'll talk about updates. Starting with insertion. In fact, this is fairly easy. Let's look at the hash structure here. So you have a lot of buckets. You have m buckets. So now you want to insert a new element. So very naturally, you ask the question, which bucket should this element go into, right? So you calculate the hash value of this element, and that's the ID of the bucket that this element will go into, right? So what do? So let's just say that it has to go into this bucket here. So this is the hash value. So you will be spending 1 IO to read the file, to read the address of the file corresponding to this bucket number I. And then, if this is the file, you would like to append this E to the end of the file. That would take another IO. Okay. So in total, it requires only 2 IOs to perform an insertion. So this is a constant number of IOs. So on the other hand, if you want to delete an element, what do you have to do? Well, first of all, you calculate the hash value of this element. So let's just say that the hash value is I, right? And then what you need to do is to find this I, okay, inside this bucket, okay? Find this E inside. I'm so sorry, I was tired. So let me do this again. So you got this hash table, right? You first look at the cell. So this is cell containing the address of the file for bucket I. Okay, I is the hash value of E, right? So you perform dictionary search there, essentially. Okay, so you find this E, and then you just remove it. Okay, as you can see, the cost is basically the same as finding this E. Okay, performing a dictionary search with the element E, right? So the cost is asymptotically the same as a dictionary search, and we have already proved that dictionary search performs a constant number of IOs in expectation. Okay, so once again, this in expectation is a sense of averaging. However, this averaging is over all the random choices made by the algorithm. Okay, what are the random choices? You still remember? We randomly chose a hash function from a family. Okay, so over all the random choices that we could have made. Okay. All right, so finally, we'll talk about something non-trivial. So this is, again, something that will involve a lot of analysis. I I will not test you on the analysis, but I require that you understand the algorithm, how to perform this overhaul and why this is important. But once again, strictly speaking, the analysis is within the scope of this course. And if you really want to get to the bottom, really want a thorough understanding of everything, then you should understand the analysis. Actually, the analysis, I would say, even though this is difficult, which is true, I would say this is accessible based on your math background. Okay. So first of all, why do we have to perform this overhaul? Hey, what is an overhaul? Overhaul is basically saying, we do everything from scratch. We rebuild the whole thing. So essentially, what this says is that we will discard our hash structure entirely, and we decide to build a new one totally from scratch. Sounds like a very drastic approach, right? So we'll talk about the analysis later. How come this is okay? However, before we go there, let's first understand the necessity behind an overhaul. Well, as I said earlier, if you have n integers, and if the block size is lambda, um, at all times, you want to make sure that the number of buckets is at the order of this n over lambda. Okay, once again, n over lambda is the smallest number of blocks that you need in order to store the input set up to a constant factor. Well, the thing is, when the value of n changes significantly, eventually you can no longer regard the number of buckets to be proportional to n over lambda. So this can happen in two ways. So imagine I keep giving you a lot of insertions. So this n goes up indefinitely, larger and larger. And so the ratio between n over lambda and m will become increasingly larger. And eventually you can no longer say that the ratio is a constant. So something must be done there. Well, conversely, the value of n can go down continuously. It gets smaller and smaller. So the ratio between m and n over lambda is going to increase again and again, unless you want to change the value of m. If you don't change the value of m, and then you can see the number of buckets will be too much for the current value of n over lambda. So this is not good because we want to make sure we have the performance guarantees that we proved. And those performance guarantees are saying two things. And one, the space consumption will have to be at the order of n over lambda. And two, the expected search cost will have to be constant. Okay. So the overhaul says that, well, whenever some special condition gets satisfied, and then it's time to do an overhaul. So overhaul is saying, I would destroy the whole hash structure, and then I will rebuild it from scratch. And how do I rebuild things? Well, simple, right? I just look at the current n elements in the data set at this time. And then I will insert them one by one into the data structure. So how much cost does this require, this overhaul require? You have n elements, and I proved earlier that every insertion takes 2 IOs. So overall, you will be requiring 2 times n IO. So that's big O of n. Okay. By the way, later, after you have already learned sorting, and then you will be able to do much better than big O of n. You will be doing something like n over lambda IOs. Lambda is the block size. But today we'll go with big O of n, and as you will see, even big O of n will be enough for us to prove prove a bound, prove the bound we want to prove. Okay, so this is the process of overhaul. Okay, so you understand whenever you do an overhaul, you destroy everything, and then you insert the current elements one by one. So now the remaining question is, when do you want to perform this overhaul? Okay, now this is the final algorithm I want you to understand. And there is analysis coming up, but you don't have to understand the analysis if you don't want to. However, this is something that you will need to understand if you want to implement it in practice. Okay. So as I said, the good principle is that you perform this overhaul after this n has changed significantly, right? For sure, you don't want to perform the overhaul too often because each overhaul would take you a lot of time. Each overhaul would take you n IOs, and n is a huge number. You really cannot do this too often. In computer science, there's this interesting phenomenon that even though occasionally I have to do something hugely expensive, extremely expensive, such as an overhaul, as long as I don't do it too often, overall, it's fine. The total number of IOs for me to support a lot of operations in total can still be proved to be something very low. All right, now to be specific about the condition that would trigger an overflow, this is the condition. So I remember when was the time I did the previous overhaul, okay, the previous, okay? So here, this value, NO, represents the value of n at the last overhaul. So this NO, so when I do a new overhaul, and then I will set this NO to the current value of n, okay? And then I move on. So the next overhaul becomes necessary only if this condition becomes true. This condition, if you ignore the ceiling, which I would ignore the ceiling now just for simplicity, essentially says that the value of n is roughly either 1.5 times NO or 0.5 times NO. So this essentially says that the value of n, the number of elements in the set right now, has increased by 50% or has decreased by 50%. And you have to pay attention that this condition may never get triggered. So for example, if you have an insertion immediately followed by a deletion, and then another insertion immediately followed by a deletion, and then the value of n will remain stable, +1, -1, +1, -1. And it will never increase or decrease. So it will trigger this condition only if the number of insertions is significantly more than the number of deletions or the other way around. All right, now let's look into this condition more closely. So this condition essentially says that in either situation, I can claim one thing. How many updates must I have since the previous overhaul, right? How many updates? So I can say that at least n old divided by 2, at least so many updates must have occurred for the next overhaul to happen. So if this is the situation, then there must have been at least 50% times 0.5 times NO insertions to trigger the next overhaul. And in this case, there must have been at least 0.5 times NO deletions to trigger the next overhaul. Okay. All right, so the next overhaul, as I said, takes big O of n costs. But as you can see, this value of n is always within a constant factor. This constant factor is at most 1.5, right, from this NO. And therefore, I'll be able to say that, this big O of n is just big O of NO up to a constant factor. Maybe this constant factor is somewhere like 2. Okay, very nice. So this is the condition for triggering overhauls. Okay, if you don't care about analysis, you can stop here. Now, for those of you that want to understand how come the overhaul is okay, and then let's proceed. Well, let's look at the diagrams, right? So this is say this is the updates, all right, and this is the time to handle the updates. Okay, so what you should be expecting is that for most updates, the costs are very low, and then at some point there will be an overhaul. This is some huge cost. Okay, by this time I mean the cost, I/O cost for handling this update. Okay, so occasionally there will be a huge spike. Okay, but on the other hand, there will be all these short studs representing the fact that most updates are handled with just a constant number of IOs, but then you will have occasionally a huge spike coming up, and this is like n IOs. All right, now this is the last overhaul. So I'm going to show you, like, for the period from this overhaul to the next overhaul, think about this blue period. Okay, I'm going to prove to you that even though I will have something very, very large here, it's okay because I will have a lot of updates during the period. And if I calculate the total cost of handling all the updates during this period, and this is pretty low. And so overall, I can say something like the total cost for handling these updates is as if every update was handled with constant IOs. So more specifically, if I assume that I have T updates in this period, so this is the T here, I'll be able to show you that the total IO cost for handling all these T updates is big O of T. Okay, T IOs for handling all these T updates. So this is not too bad, right? Because every update, if you think about it, even if you just pay one IO for each update, you already have T IOs. Now, I'm showing you that even with the overhaul, even with this huge spike, the total IO cost for handling T update is still big O of T. So it will be slightly higher. Before it was a constant, and now it's still a constant. However, it's maybe a slightly larger constant, and this is the objective. So let's do the analysis. On the previous slide, I already explained that this T, once again, this is the number of updates in the blue period between two overhauls, right? So I already proved to you that, the number of updates is at least NO over 2, right? So remember this NO, as you can see here, is the value of N, at the last overhaul. So processing all these updates requires big O of T IO. So here it counts for all these short studs. Okay. But on the other hand, in this blue period, I also need a very large cost for handling the overhaul, right? So the last overhaul finishes in NO IOs, right? This is something I said here, right? Okay, because when you do an overhaul, the current size N is within a constant factor of the value of NO. Okay. So now if you add up these two costs, this represents the total cost in this blue period. All right, now let's do some calculation. I've already explained to you, every time you see this big O, always think about it as less than or equal to, and then some constant. All right, so this is what it says here. Every time you see this big O, always think about it as less than or equal to some constant, C2, right? So this is C2 here. So essentially, we're saying that the total cost for handling all the updates during this period is here. Okay, so now you can look at this NO, the relationship between T and NO. And now you can see this NO is bounded by 2 times T. right? So this is why you are able to derive this inequality here. So what have we shown? We have shown that in this period t, okay, so even with the overhaul, you will be doing at most C1 plus 2 times C2. This is not too bad, right? Because even if you did not have the overhaul, you will be already doing C1 times T. But now you are just doing C1 plus 2 times C2. So the total cost is still proportional to T. You might as well say that, well, in terms of total cost, on average, it's like every update has performed slightly a higher number of IOs, and this is still bounded by the constant. Very nice. So this is the last slide of today's talk, today's lecture. It's a difficult lecture, and also it's a long one. So here, essentially, we have proved a powerful theorem. The theorem says, look, suppose initially the data set is empty, so it's S. And then we're going to maintain a hash table over a sequence of insertions and deletions. So this can be an arbitrary sequence, insertions mixed up with deletions in an arbitrary manner. Okay, so if n is the total length of the sequence, and then you are able to prove that in total, in order to perform these n updates, these n operations, the total I/O cost is big O of n expected. So as I said, this is the effect is as if every insertion and every deletion costs you a constant number of IOs in expectation. Okay, so this is the theorem. Well, finally, just so you know, in computer science, whenever you have something like this, we want to say something more concise. So it suffices to say that every update is amortized a constant number of IOs. So this word amortized is essentially another way of saying in total, with n operations, you'll be using n IOs. Okay, so as I said, the effect is as if every update pays a constant number of IOs. So this is the meaning of this amortized. So I hope you can understand the difference between amortized and this expectation. So this amortized is amortized in this sense, but the expectation is over all the random choices that are made by the algorithm. All right, class, thank you very much for your attention. Indeed, it's a difficult lecture. I understand that. I hope this video has been useful to you, and I would see you in the classroom. Okay, bye-bye. Take care.